Hello. I see that many of you are here. And then the host of this Zoom meeting, which is good. That means that I can share screen with you guys if I need to. So the course is going to start in a few minutes. Okay, welcome everybody. Welcome to this course, Electromagnetic Field Theory, ECE 604, presented at the university here, Purdue University, for spring of 2021. I have taught this course for quite a few semesters now, and I also have been in this area for a few decades. So if you have any questions on electromagnetic field theory, feel free to ask, because I should have the knowledge to answer most of your questions. Well, I have a few handouts that I like to give to the students of this course. The first one was the course outline that I have shared with you. Okay, you can look at the course outline, and let me see if we can find one here. But never mind, you know the course outline. I'll share it with you next time. The next handout I had was the questionnaire. Okay, and I like to fill out the questionnaire and hand that back to me so that I can know you better and how to orient my lectures better, knowing your background and what you like to work in and so on. The lectures will be presented on Zoom through PPT slides, and I will usually hand out a copy of the slides after the lecture. And I have also been handing out lecture notes in the past. Usually after the first lecture, I take the lecture notes from the previous semester and see how I can polish and improve them, and then update the lecture notes and hand them out to you not long after the first lecture. If you like to look at the lecture notes beforehand, you can Google my name, Chu, and then Purdue University, and put ECE 604. You will find my homepage where I have all the materials from previous semesters posted on the Purdue website. Okay, so I'll let you do some adventuring with that. The course is long, I would say, difficult. Many students complain that it's difficult, but I hope that you will find the course rewarding, because you will learn lots of things from this course, almost 150 years of electromagnetic field theory. I cannot teach everything in the class lecture hours, so a lot of the learning is done through the homeworks. I would advise you to do all the homeworks because you will learn lots of things by doing the homework carefully and learning from doing them. So there are also PAs around. I have a few people in my research group, Bo Yuan Zhang, Jie Drew, and Ivan Omatowski, who are willing to help out with this course. And occasionally I have to have Dr. Dong Yap Na substitute for me for this course because of I have other commitments, like other meetings and so on. I don't have to travel so much these days, but I still have to attend some other important Zoom meeting because like the beginning of February 1st, I have to attend a National Science Foundation review panel the whole day. It's a full day meeting, so I had to ask Dr. Na to substitute my lecture for me on that day. So let's begin with the simple question. Why study electromagnetic field theory? It is in fact a very old theory, 150 years old, but new ideas are always emerging in this electromagnetic field theory. And you will find that this knowledge has a very long half-life. If you learn this knowledge well, you can actually keep this knowledge for a long time in your mind, hopefully, or in your soul, so that you carry this knowledge with you that makes them useful to you in lots of ways as engineers. And I was just learning the other day that a patent lawyer is also signing up for this course. And even if you want to understand patents, it's good to learn about electromagnetic field theory. One thing sure about electromagnetic field theory is that it is very pervasive. It has influenced modern technology so much that you find electromagnetic field theory in all sorts of technologies that we are working with. So let's study the key reasons as to why electromagnetic field theory is so important. And electromagnetic field theory is, of course, based on Maxwell's equations. There are 4 of them. And I presume that you have had an undergraduate course before you walk into this course, because with that assumption, I'm going to gloss over some of the details of which I hope you have learned from your undergraduate course. So the first thing is that electromagnetic theory is valid over a vast length scale. Can you see my slide and my pointers? Hello?
Yes, yes, Professor.
Yes.
Wonderful. You can see my pointers. I'm going to use this as a pointer. Otherwise, I have to activate another pointer somewhere. Okay, but this cursor can act as my pointer then. Electromagnetic theory is also valid over a very broad frequency range. Because of this theory is valid from subatomic length scale or dimension to galactic dimension. Things that happens inside the atom, like how an electron moves around an atom, is governed by electromagnetic theory. And how we communicate with the outer galaxies, looking at the supernova events or whatever explosions, electromagnetic radiation that comes from outer space. Those signals come to us through Maxwell's equations or the use of Maxwell's equations. Because of that, electromagnetic theory is valid from static to ultraviolet. Static has very long wavelengths. You probably learned in your undergraduate course that if you have a wave of frequency f, okay, and then the lambda is c divided by f. I think this you learned from your undergraduate course. So the lower the frequency, the longer the wavelength. The higher the frequency, the shorter the wavelength. And if you go through ultraviolet, one of the current technology that is very useful in the industry is 193 nanometers. Okay, and of course, when you're working with very low frequency signals, the signals are on the order of miles and kilometers. So you're talking about wavelengths on the order of Mars. Very, very long wavelengths if you're dealing with a very low frequency. And electromagnetic field theory or Maxwell's equations can still be used to describe those physics over this vast range of dimensions. Okay. Another thing very important about electromagnetic theory is that it is relativistically invariant. This is a special case about special relativity. If you have studied that before, it was put forth by Einstein in 1905. What it says is that Maxwell's equations look the same no matter what inertial frame you are in. Inertial frame is the frame that moves with the velocity v. You probably have heard that if you have a rocket ship moving with the velocity v, all the dimensions in the rocket ship would shrink or compress compared to the observer in another inertial frame where the velocity is slower. Clock also slows down in a fast moving inertial frame. But Maxwell's equations look the same, whether you are in a rocket ship that moves close to the speed of light or whether you're in the rocket ship that moves very slowly. That is what we call relativistic invariance. And what is very important is that in 1920s, Dirac actually postulated quantum electrodynamics, or QED. And we found that Maxwell's equations can still be used there to describe a lot of the physics in quantum electrodynamics. Hence, if you were to study Green's function, and a form of Green's function that you will learn in this course is the dyadic Green's function. And this Green's function is valid even in the quantum regime. Because of the validity of Maxwell's equation in the quantum regime, scientists are avidly studying this field called quantum optics, where you try to incorporate quantum effects into classical optics or classical Maxwell's equation. And that won Glauber Nobel Prize in 2005. He did this work in 1968. He had to wait a long time before he got his Nobel Prize. And if you are a mathematician, you might be interested in the fact that Maxwell's equations are in harmony with differential geometry. Differential geometry is a new kind of modern calculus put forth by this Frenchman Cartan in around 1945. And you will learn that in this course, we used a lot of calculus that came from the 1700s. People like Stokes, Cauchy, and those mathematicians put forth a very ancient or old-fashioned kind of calculus. But Cartan showed that there is a new kind of calculus called differential geometry. And Maxwell's equations can be described using differential geometry as well. And those are called differential forms. And differential forms inspire Yang-Mills theory. And one of the things that if you were to read widely, one of the quotes from Misner, Thorne, and Wheeler's book is that differential forms illuminate electromagnetic theory, and electromagnetic theory illuminates differential forms. So they synergize with each other very, very well. And electromagnetic theory is also one of the most accurate theory in the world, in this universe. We hardly know of any other theory that is that accurate because it's been tested to a few parts in a trillion. And I think Feynman said this in 1985. At the time when he made this statement, it was a few parts in a billion, I think. What it amounts to is that if you were to have an airplane flying from New York City to Los Angeles after a 6 hours flight, and if you make an error of a few parts in a billion, the error on the other side is just a millimeter or so. So that is one what a few parts in the billion is, and a few parts in the trillion is even more accurate. It has something to do with the fact that if you shoot a laser beam into the moon's surface, it just makes a very, very tiny spot on the moon's surface. That is what a few parts in the trillion is. Of course, because electromagnetic theory is that pervasive, it has impacted science and technology in electrical engineering, in particular optics, wireless and optical communications. Every one of us carry a cell phone, but you have to be mindful and wary of the fact that the signals that you are using in your cell phone is an electromagnetic signal, because the cell phone has to leave your handphone by a wave nature of electromagnetic theory, and those are usually around a few gigahertz. You will learn what gigahertz is. And then the wave travels to your base station antenna, and then from your base station antenna, there is a network of antennas connected all over the globe, and some of them might even talk to the satellites. And some of them might even be talking to low Earth orbit satellite. I think it's called low Earth orbit satellite. They're putting a slew of satellites very close to the Earth surface, so that in the future, our IT cell phone can communicate with them. And that communication is done through electromagnetic field. Of course, computers uses electromagnetic signal. If you do remote sensing, the fact that you have weather forecasts, the fact that microwave, which is the bread and butter of remote sensing, can see through cloud. So even when the Earth surface is thick with cloud cover, we can see what is happening using microwave remote sensing. Of course, we cannot see with microwave with our own eyes. Our eyes use the visible spectrum, but the microwave spectrum can be detected with new technologies that we have invented. Of course, we have subsurface sensing, where you look for hydrocarbon in the Earth, and that usually is done using electromagnetic signal as well. Of course, you use seismic, acoustic, and other kinds of sensing modality, but electromagnetic subsurface sensing is an important component of that technology. And of course, in bioelectromagnetics, where we are using electromagnetic signal to probe as to what is happening inside the human body. And of course, one of the things that is very hot in bioelectromagnetics is the pacemaker. Many old folks have to wear pacemakers to maintain their steady heartbeat, so that they can have a longer lifespan. And in order to communicate with those pacemakers, you use electromagnetic signal. And in fact, they are inventing a new variety of pacemaker that can be recharged wirelessly, or you have wireless power transfer, or wireless power transfer from some source into your pacemaker gadgets inside the human body. And that can avoid having to open your body up in order to charge up the signals inside, or the battery that is inside your pacemaker. So as I said before, electromagnetics has an enduring legacy. And I make a slide like this when I was a young man, and the slide pretty much remains the same. I just have to add a few items. Maybe more recently, I have to add things like quantum optics, cosmic force, quantum information, and maybe things like nanotechnology and nano-optics. Those are the recent inventions, because nanofabrication is one of our new gifts, because we can make things so small now. They are on the order of nanometers. A nanometer is, of course, a dimension much smaller than the size of a biological cell. But actually, the virus that is attacking us actually has the dimension of a few nanometers. So life form exists down to the length scale of nanometers. Okay, and one of the things that is very recently small antennas because of the cell phone industry. When I was a young man, there were no cell phones around, not as prevalent as it is now. At the time, we have to carry a brick as a phone if it is a portable. It was a portable device, but now you can carry your cell phone in your pocket because of advancement in technology. And we have to make the antennas really, really small in order to make things portable or highly portable. And there are a lot of other things. EMI stands for Electromagnetic Compatibility and Electromagnetic Interference. This topic is very important in the cell phone industry because of the fact that we are packing a huge number of devices into a cell phone now. And those electromagnetic devices interfere with each other, and we have to know how to cope with this interference. And you probably have heard that our cell phone now has about 6 billion transistors to maybe 60 billion transistors. So you can imagine the number of transistors we have in a cell phone is larger than the population of the human population of the whole Earth. Okay, so let's look at a brief history of electromagnetics and optics. In the beginning, it was not known that the field of electricity and magnetism, which is what this left column was called, is the same as the field of optics. They were governed by the same set of equations. Okay, so the field of electricity and magnetism has a rather long history. Of course, the Chinese figured out how to make compasses, and lodestones was discovered in prehistoric times. The Greeks knew about static electricity, but it was not until the invention of the telegram, the fact that we can send signals using two pieces of wire, that piqued the interest in telegraphy. And because we have to understand telegraphy really well, then we have to understand this technology really well. And there's another field that actually pushes this technology, which is electrical machinery. Electrical machinery was invented around the 1830s. Okay, because of all this need by us, Maxwell's equations were completed in 1865. 1865 is an interesting year because that was the end of the American Civil War. I believe that was also the year that Lincoln was assassinated. So you can see that it was about over 150 years that Maxwell's equations were completed. But it was thought that optics was a different field before these equations were completed. But if one stares hard at these equations, you can actually get all the physics of optics from Maxwell's equations as well. So the work of Maxwell unified these two seemingly divergent and very different fields. Of course, you have pinhole camera invented by this Chinese philosopher Mojer in 400 BC, and then this Islamic scientist Ibn Sa'd actually knew how to make lenses and eyeglasses, and he knew about the law of refraction in the 900s. Snell's law came about in the 1600s, of course. There were lots of mathematical work on how to describe optics properly throughout these few decades or few centuries of studying optics. And once Maxwell's equations was proven to be a unifying theory between optics and electricity, then many mathematicians came on board to study these equations. So you have people like Heaviside Hertz, whose name still rings in your mind, because when you go to a computer, buy a computer, we have to understand how many megahertz or gigahertz a computer is running at. And there are many unsung heroes. You will learn about them in this course. And quantum electrodynamics, as I said before, was not invented until 1927. And many researchers collaborated on this, and these four persons, I believe, including a Japanese scientist, Tomonaga, was given the Nobel Prize. And then we have electromagnetic technology, and it's spurred by the fact that we have nanofabrications these days. We can make things down to nanometer dimension due to the lithography processes that we're using. We can make, the last time I heard is that we can make transistors as small as maybe 5 nanometers. I was told that Samsung is probably the leading player, and then there's another Taiwanese semiconductor company, TSMC, Taiwanese Semiconductor Manufacturing Corporation, that can make things of that dimension right now. And another very important advancement that we have is our ability to detect single photons. Single photon, as you will learn later in this course, has to do with the quantum theory of light or quantum electromagnetics. The fact that we can measure single photon means that the particle nature of light or electromagnetic field becomes highly important, and we have to understand the electromagnetic theory from a quantum viewpoint. And because of that, quantum optics and nano optics became very important after 1980s. And there was a watershed experiment done in the 1980s. Okay, and that experiment disproved Einstein's assertion that there was a hidden variable involved in everything that happens in this world. Okay, that Frenchman who did the experiment was Alain Aspect. And because he proved Einstein to be wrong, then what it emerged is that there's a new field called quantum information science, that you do not know the outcome of an experiment until after the measurement. So before a measurement is done on the system, quantum theory says that you don't know what state the system is in. That is actually highly marvelous in my opinion. What it says is equivalent to stating the fact that our karma is not written on our forehead the moment we are born. We have the future of ourselves in our own hands. Okay, and that is what quantum information is all about. It's not predictable until the measurement is done. And then, of course, we have the emerging field of quantum electromagnetics and optics, and we're still discovering new knowledge in this area. Okay, any questions so far? If not, then let's revise something that you have learned in your undergraduate course. Maxwell's equations in integral form. You probably have seen that. And then we can write them down. And then you have static electromagnetics. And then we have Coulomb's law, electric field using Coulomb's law, and then Gauss law, and so on. So let's revise what we have in terms of Maxwell's equations in integral form. Okay, I hope this is not new to you. Okay, we can start with Faraday's law. Okay. Faraday's law is the statement that if you were to take the electric field and do a line integral, this is a symbol for line integral over contour C. Okay, that contour C might look something like this. Okay, and the electric field might be something like this. And then that should be equal to the time variation of the total flux captured by this loop. And let's assume that the loop captures a surface area S, and there will be electromagnetic flux B that goes through that surface S, and B dot S is the measure of the flux going through a very tiny surface. And if you were to sum that up, look for the time variation of that, then the left-hand side is the voltage. Okay, this would give you, if you remember Kirchhoff's voltage law, this integral will give you the voltage at the loop. And this is Ampere's, Faraday's law, sorry. And we have to assume that partial B, partial T is not equal to 0, and we will have this induced voltage. And this idea can be generalized to multi-turn circuits. And if you have multi-turn circuits, if you have a B flux going through this multi-turn circuit called a solenoid, then that B would induce a higher voltage, V, at the solenoid, or this is also an inductor. Okay, that is our knowledge of Faraday's law. And then, of course, we have Ampere's law that you have learned in your undergraduate course. And this is a statement that, well, if you were to integrate the magnetic field around a loop, okay, a C, and there's a magnetic field H there, and that this integral would be the same as the integration of the current. Okay, sorry, I shouldn't put the closed loop over here. There's not a closed surface, so the surface is not closed. Okay, so similarly, if I have a current J going through this surface S, and I can calculate the total current that is cutting through that surface S, and there might also be electric flux. Okay, the electric flux contributes to what is called the displacement current, and that part is computed or calculated using this formula. It says that the electric flux and the current, when integrated, will give you a value, and that value is the same as integrating the H field around a loop. And if you apply this thing in a very simple fashion, and this is what usually done in the undergraduate course, is that if you have a piece of current, a piece of wire carrying a current, and that current generates a magnetic field, you can use this formula to find the strength of the magnetic field induced or given by this current that is carrying in a piece of wire. Okay. Those are the integral forms. Let me see. Let me go to Coulomb's law then. Ampere's law, then we have Coulomb's law. Coulomb's law, which sometimes is also called Gauss law. Okay, I think I would rather give the credit to Coulomb, because you can derive this law from his original Coulomb's law. Then this law says that if I have magnetic flux, not magnetic flux, sorry, electric flux D, and if I were to integrate that over the closed surface, that integral should be equal to the total charge inside that closed surface. Let's imagine the closed surface S, okay, and that you have some charge Q inside. This Q will produce electric flux, okay, to produce electric flux. And you can calculate the flux through all this surface by performing the integral on the left-hand side. And if you add the total flux up by the calculation of the left-hand side, that should be equal to the charge Q that is enclosed by the surface S. And you have another Gauss law. Or B field, okay, which says that B dot ds is equal to 0. And this is always equal to 0, meaning that whatever goes in must come out. This is a B field. Okay. This is the same statement as there's no magnetic charges in this universe. Okay, there are no magnetic charges in this universe. It's also the same statement as saying that whatever goes into a surface S must come out of that surface S. Okay, just like what you have inside the house. If you have the windows in your house opened, then whatever goes in must come out. Okay, so I like to emphasize that static electromagnetics can be obtained from your original Maxwell's equations written in integral form. So if you were to have that statement again, that then you have Faraday's law, that before that you have the flux linkage on the right hand side, you will have this for Faraday's law. And then you have Ampere's law. And then it will be just J dot ds. This should be a single integral. Okay, this would be, and the displacement current term disappears. Again, just rewriting this law that I have written. This thing goes to 0. This thing goes to 0 when you have static, but this term doesn't go to 0. So what you have is something that looks like this. Let me put a circle over here to indicate that it's a closed loop, and this is the total current I that goes through a loop. Okay, so if we have a loop, and then there's the total current I that goes through the loop, then the magnetic field H must obey this law. And of course, you have things like B dot ds. And I guess we can use double integral to integrate a surface integral. And this is always true. So this is static electromagnetics, or 4 Maxwell's equations in static term. And it might be interesting to study Coulomb's law again. Coulomb's law, the way it was given. Okay, it was actually a very old law. It was discovered in 1785. What it says is that if you have two charges, Q1 and Q2, and then they are separated by a distance R12. Okay, or let's just call it R to be simple. Separated by a distance R, then the force between these two charges, this force is a vector, so it has the direction, and it's proportional to the size of these two charges divided by 4 pi epsilon. Epsilon is the permittivity, okay, something that you should have learned in the undergraduate course. And then there's an R squared at the bottom. And then there's this unit vector. I will use a hat to denote unit vector. And this unit vector is a unit vector that points from 1 to 2. Okay. What this is saying is that there's a force pointing from charge 1 to charge 2, or Q1 to Q2. And that force is given by this formula over here. And that was discovered by Coulomb long ago, where you can also write the unit vector in terms of position vector, R2 minus R1. okay? And then divided by, I hope you are familiar with this notation, that this just means the magnitude of R2 minus R1. And then I hope you know how to subtract two vectors. Say if you have one vector R1 and this is the origin, and then you have a second vector R2. Okay, R2 minus R1 is the vector that points in this direction. And I hope you have done that in your undergraduate course before. And then, of course, if you normalize by this, this would be the distance. This distance here would be just given by that. And if you normalize by that scalar constant, you get a unit vector, okay? Hence, you can also write this force expressed by Coulomb's law to be Q1, Q2 over 4 pi epsilon R cubed. You can put a cube in the denominator, but put this two R2 minus R1 in the numerator, okay? Where you can say that R2 minus R1, the magnitude of is just equal to R. So this was Coulomb's law. And actually from Coulomb's law, you can say quite a bit of things. You can say that if I express this to be Q1 and then Q2 is the lump of charges. Q2 is delta Q. Let's assume that we have a lump of charges here. And then you can write the force F to be pointing in the R hat direction, which is from 1 to 2 in this picture. And then the two charges are Q. Okay, let's assume that this is Q1 is Q, Q2 is delta Q. You can write Coulomb's law for this geometry to be something like this, R squared. And then you can define the notion of force per unit charge, that the force on Q2 is proportional to the electric field times the total charge Q2. And that will give you the notion that there's an electric field E, which is given by the force experienced by the charge Q2, normalized by the total number of charges you have. And that would give you the formula for the electric field, R hat. And of course, you can write this in a notation that is more compact and slick. And you can write this as R1 minus R1 prime. Okay, let's assume that this is R prime, this is R. And then you can use this rather slick notation to write this force. Okay, and this is a nice way to write things in coordinate independent form, where this point is R, this point is R prime, and the charge Q is sitting here, and there's an electric field that is coming out from this charge Q, and that electric field is given by that notion, and this distance is given by R minus R prime magnitude. Okay. So let me also make the statement that you can derive, let me see. You can also use this concept for a cluster of charges. So if you have a cluster of charges, instead of just a point charge, okay, Q, which is a cluster of charges, then the electric field due to this cluster of charges, which is actually a linear superposition of point charges, we can use the principle of linear superposition because electromagnetic theory is linear. Okay, each of this point charge has a charge of Qi, and the charge is located at Ri. And then you can have the rest of the thing down in the denominator. So this is written in the form that is been summed over the amplitude of the charge, its location, and you write this electric field, which is the total electric field that you observe if you're out there. Okay, the electric field will look something like that. And then you can also use calculus notion that Qi is actually the charge density. Yes, any questions? Anybody have? Okay, somebody has a question, or you want to mute your mic because I'm hearing what you're saying. Anyhow, so you can have this thing over here. And then if you replace Qi by that thing, then this will become I equal to 1 to n, and then rho of r sub I, delta Vi, r minus Ri over 4 pi epsilon r minus Ri. Okay, so then you have the general notion that the electric field at the point R, observation point R, can be written as an integral. As you make this thing very, very small, very, very tiny, you can think of this as a integral. And then you can write this in calculus notation, which is in a sense more elegant. Okay, where V is the volume that the charges are residing in. Okay, so Coulomb's law is actually very powerful. You can actually derive Gauss law from Coulomb's law, and usually this law is called Gauss law, and is completely derivable from Coulomb's law. Say if you have a point charge Q, it gives out electric field, and then you can calculate the electric flux. Okay, you can calculate the electric flux that this point charge is giving out. You can actually draw an arbitrary surface around this thing. If you draw a circular surface, it's quite easy to convince yourself that if the surface is circular. Okay, if this surface is circular, it's quite easy to convince yourself that if I use Coulomb's law in the previous slide, okay, and calculate the electric field in this manner, or in this manner, and that because of the R squared dependence here, you can show that this integral always is the constant irrespective of the distance from the origin. And hence, this integral always gives you the charge Q inside the surface S, if it's circular. But you can easily show that even if you change the shape of the surface, the flux that you calculate cumulatively is still equal to Q, the charge enclosed by the surface S. Hence, you can actually use Coulomb's law to start with and derive this Gauss law. And I would like to actually call this Coulomb's law because it's derivable from Coulomb's original law. Okay. And I guess stop here. Of course, you can also prove very easily that this is equal to 0 quite easily, because whatever comes in must go out. That is the physical meaning of this Gauss law. This is Gauss law for. And some people write Gauss in this manner, but no matter how you want to write it, it's fine with me. Okay, it's Gauss with a single apostrophe, or a Gauss with the S following the apostrophe. Are there any questions? I guess you can do the reading from the lecture note. If you don't have the lecture note, you can actually go to my website and download the lecture notes from last semester. They are pretty much the same. And some of these details are discussed in the lecture note more carefully. Any questions?
Yes, if we don't have a background in like electrical engineering, like a lot of these topics in the first few chapters of the book that you have on the syllabus.
Oh, okay. If you don't have a background in E&M or electromagnetics, I encourage you to study my undergraduate lecture notes. I wrote a whole bunch of undergraduate level lecture notes when I was teaching in Illinois, and that is ECE 350X. I think it's also in the link in my homepage at Purdue. And you can read those lecture notes to brush up your background. And if you, do you have a background in electromagnetics and not at all? You know, if you have a freshman physics course, if you take a freshman physics course, I remember that Halliday and Resnick is a good book to read if you want to understand EM, but that was at the very elementary level, I remember. But even if you don't have that, it will be very difficult for you to follow this course. And this course requires prerequisite of an undergraduate EM course taught in most electrical engineering department across the country. If you have a physics course, undergraduate physics course, that should help too, because they also teach you quite a bit of things in undergraduate physics course. Okay, and there's this person writes a very nice physics book. Let me see, what is his name? If you're from the physics department, you might want to read this book by David Griffiths. He writes very well and very lucidly. Okay, he's from the physics community. And of course, if you're from the electrical engineering community, you might want to read the book by David Cheng. Okay, he writes some EM books at the undergraduate level. Okay. I can give you the citation for these 3 books if you're interested by email. And then you can read from there. If you truly don't have a background in undergraduate EM, and if you truly don't have a background in undergraduate EM, you will find this course tough going. Unless you're a genius. Of course, you're a genius. Nothing is difficult for you. Okay?
Thanks.
Okay, I'll let you go then, because it's 11:20. I'm supposed to teach until 11:20 to allow you time to walk between classrooms, but we don't have classrooms to walk between now, I suppose. You probably are attending this from your home. So if you have any questions, and if you want to use the remaining time to ask me questions, I'd be happy to answer them. Okay, if not, then yeah, I'll let you go. Okay, is that fair?
Thank you, Professor.
Okay, I'll let you go and see you on Friday then. By the way, I gave out weekly homework. It would be nice if you can do the homework, because it is from the homework that you learn a lot of things. Okay?
Okay, Professor, thank you.
Okay, I see you later.
Bye.
Bye-bye.